What's up, cool kids? We're doing related rates in the hizzy. It's Mr. Williger and his little partner, June Twilliger in the house. It's getting pretty bright in here with all the calc we've been doing, so we gotta put on our shades. Okay? Oh, you can see without them. Okay, guys, we were looking at related rates part 2. RR part. Oh no, computer.
Oh no.
Part 2. Okay? We're gonna do 2 problems and then call it a day. Right?
Yeah.
Yeah. Okay, so let's say there's a balloon. June, what's a balloon look like? Is this a balloon? Is that a balloon? Yeah. Is that a smiley face? Yeah, so you have a hot air balloon rising up from a lever, and it's being tracked by someone named Henry, who is 700 feet away from the liftoff point. At the moment, Henry finds the hot air balloon at an angle of elevation of pi/6. The angle is increasing at 0.16 radians per minute. How fast is the balloon rising? How fast is it, June? Can you count? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Is that the end? Whoa, what did you do? Uh-oh. Do you think Dad should take over the calc? Yeah? Say bye-bye. Say bye-bye. Stop poking yourself in the eye. Say bye-bye. Bye-bye. I'm back. So we have someone holding the balloon. How happy they're holding a happy balloon. Well, it's a hot air balloon, so hopefully they aren't holding it. So it's rising straight from a level field, right? It's being tracked by someone who's 700 feet from the liftoff point. Well, number one, what are we looking for? We're looking at how fast the balloon's raising. So if we call this h, the height, we're looking for dh over t. Everybody's a critic in this house. Anyway, so number 2, I already started drawing the picture. He's going to be 700 feet away from the balloon, right? And this angle is going to be pi/6. Because we're in radians. Good old radians. Okay. So, how do all these things relate to each other? Well, if I call this h, this is the distance away from it, right? Which is 700. This is going to be constant. Because he's not going to run away from balloon. He's just standing there watching the magnificent balloon float in the air. Okay? But we do know how fast the angle's changing, right? So if I want to relate these things, could I do tan of theta equals your height, which is your opposite, over 700, because 700 is constant? You could do that. Well, actually, that's number 3. I made the equation. So number 4, what I'm going to need to do is take what? Derivative of both sides. In fact, why am I not finding h right now? Pause. No, it's because I don't have to. So before I take the derivative, I'm actually going to multiply both sides by 700 to make my life easier. Okay, so now I'm going to take, because of number 4, I'm going to take the derivative of both sides, oh no, in terms of t. So this becomes 700. What's the derivative of tangent? Everybody wants. Secant squared. Times your derivative of theta over time, right? Okay. Now this side just becomes good old dh over dt. Right? Alright. Okay, and that's what I'm looking for. That's what I'm going to be looking for, so this works out well. So number 5, I plug in what I know. Okay. 1 second, guys. I gotta see something. Turns out I just need a faster computer. Just can't hack it. Okay. So this is still 700. Secant squared. Now my angle is pi over 6 in radians, right? I know that because the problem told me that. Times, what was my d theta over dt? It was 0.16 radians per minute. Okay. So I plug that in for my d theta. And I plug this all into my handy dandy calculator, and I get 149.33. Okay. Now 6, to interpret this was in radians per minute. This is in feet. So this would be in feet per minute. 149.33 feet per minute is how fast the balloon is rising. Okay? Okay. Oh no. Okay, one more. Last problem. You have a conical tank, that's 12, that water's rushing out at 12 feet a minute. The tank stands point downward, height of 12 feet, and has a base radius of 9 feet. How fast is the water rising when the water is 8 feet deep? Okay, good question. So, number one, what are we looking for? We're looking for how fast is the water rising, right? So, I'm actually going to do this. I'm going to draw my picture. It's a cone, conical. There's some water in it, right? And we're looking at the height of the water. We're looking at the rate at which the height of the water is changing. Okay? So again, here's my cone, right? The base radius is 9 feet. The height is 12 feet of the cone. The water is going to be 8 feet deep at this current time. This is going to be some other radius. Do you have everything I need? Yeah. So first thing I'm going to need to do is find this length right here. Okay? And to do that, you know what I'm going to use? Similar triangles. See the big triangle? See the smaller triangle? Do you see where Calc is kind of, you have to know a little bit of everything and go back and use it to get points that you might not have known? Some of you guys are going to hate this section. It's a fiery passion that consumes your soul. Okay, so we got to find this radius when the height's 8. Well, I'm going to set this up 9 over 12, because that's my big triangle, equals my radius over 8. Radius coincides with the 9, 8 with the 12. Okay? Okay. So then you cross multiply. 72 equals 12r, right? So r equals 6. So this is 6. Right? Right? Okay. So now I have that's my 6. Here's a formula I'm going to be looking at. Volume equals 1/3 pi r squared h, right? Right. In this problem, the water's running out at 12 feet cubed per minute, right? So that means our volume, our dV over dt, is negative 12, right? Because we're losing it. Feet cubed per minute. Okay. We're looking for DH. Now here's going to be a problem for us. Well, besides the whole thing's a problem. When we look at this, when we take this derivative, right, we aren't going to get a DH. We don't know, I mean, we're going to be looking for DH, but we don't know what the change in radius is going to be at a given time, okay? We have no way to figure that out. So what I'm going to do is propose this. This is going to be, you guys aren't going to like this problem at all. If my R over H, this is just a sidebar. If my R over H equals 9 over 12, my radius over my height, right? And it's always similar triangles like we showed before. Then I could change this to 3/4, right? And multiply both sides by H, and you could get R equals 3 over 4H, right? I'm going to really blow your guys' minds here. Ready? I'm going to take this, okay, and plug it in for R. So my volume actually equals 1/3 pi times 3H over 4 squared times H. Okay? Sorry, I gotta sit again. My knees, they're getting old. Okay? So, what happens to this equation, I'm going to put that squared through to everybody. I get 1/3 pi times 9H squared over 16 times H. So this and this cancels. And you get 3 pi over 16 times H cubed equals your volume. Now I got, in terms of variables I know, none that I don't. So now I'm going to take my derivative of both sides in terms of t. You got to respect your variables. So you get dv over dt equals, now 3 pi over 16 is just a number. So for the h, it becomes 3h squared, right? Because remember, pi is just a number. It's not a variable. So this is actually 9 pi over 16, oops, times dh over dt. Can't forget about that guy. Okay, h squared dh over dt. And now we plug in what we know. Oh, by the way, this. Okay, one sec. Okay, so now we're going to plug in what we know. Well, dv over dt is negative 12. 9 pi over 16 times our height was 8. Right there. Okay. Times dh over dt. Okay. So this becomes, how did I do some of this stuff? Oh, that's odd. I multiplied everything by 16. And I got negative, uh-oh, what's that water flowing on? Runs into the tank. Oh, man, that's doing a different problem. So that's positive. Positive. Water's running into the tank, not out of it, silly goose. Okay, so this becomes 9 times 64 times pi dh over dt, right? So we divide both sides by whatever this number is. Ditto. And you get 0.106 is your dH over dt. And that's going to be feet per minute. So if you look at the problem, everything's feet per minute, right? So at that point, the height was rising at 1.106 feet per minute.